Hello students, in previous video we have derived an expression for root mean square value of alternating current. Now in this video we are going to find root mean square value for an alternating EMF. So first of all we have to define what is the RMS value of an alternating EMF. So similar as the case was in alternating current, if we take a circuit having resistance only and we connect that to an AC source. Now we know that whenever there is a source and a current is flowing in the circuit and EMF, an alternating EMF is set up across it, then in that case some heat is produced here in the circuit. That heat get dissipated because of the flow of current. Now to define RMS value of alternating EMF, what we are doing, we are replacing this EMF source, this alternating EMF source, to a steady source. Now steady EMF source is a battery or a cell, so we are replacing it with a steady source, a DC source. Then there exists a steady voltage. Now we find that voltage which can produce same amount of heat in the same time as was done by the alternating source or alternating EMF. So alternating EMF लगाने पर जितनी हीट हमें जितने टाइम में मिली थी, सेम उस टाइम में उतनी ही हीट कितना स्टडी वोल्टेज अप्लाई करने पे मिलेगी, दैट वैल्यू ऑफ स्टडी वोल्टेज इज कॉल्ड root mean square value of an alternating EMF. So we can define this root mean square value as the value of a steady voltage that produces the same amount of heat in a given resistance as is produced by the given alternating EMF when applied to the same resistance for the same time. This is the important thing, that resistance and time should be same, to the same resistance for the same time. That value is called RMS value of an alternating EMF. Okay, so now we are going to calculate the value or find the expression for it in terms of its peak value. So basically we are going to find the relation between epsilon RMS and epsilon नॉट, इन दोनों के बीच का रिलेशन हमें डिराइव करना है. सो फॉर दिस वी आर अज्यूमिंग दैट एन अल्टरनेटिंग EMF epsilon is applied to a resistance capital R, and this EMF is given by epsilon is equal to epsilon naught sine omega t. So this much alternating EMF is applied to a resistance R. Alternating EMF epsilon is applied to resistance R, okay, and its value is epsilon is equal to epsilon naught sine omega t. Now the heat produced because of that in a small time dt, heat produced in a small time dt can be given as dH is equal to, in terms of EMF the value for dH is epsilon square upon R dt, and epsilon की जगह हमें सब्सटीट्यूट करना है epsilon नॉट साइन ओमेगा t का स्क्वायर upon R dt. So dH will be epsilon naught square upon r sine square omega t dt. Now to find the total heat produced in time period capital T, we have to integrate dH, that means this whole integral, within the limits of t from 0 to capital T. So let capital T be the time period of alternating EMF, then heat produced in time capital T is H is equal to integral of dH, that means integral of epsilon naught square upon r sine omega t dt, and within the limit 0 to capital T. Okay, so this is the value of H. Now we have to solve this integral. To solve this, we get H is equal to epsilon naught square upon r. These are constants, these cannot be integrated, so we have to integrate, this is sine square, we have to integrate sine square omega t dt, and for it we have to use the formula sine square theta is equal to 1 minus cos 2 theta upon 2. That means it will be is equal to epsilon naught square upon r 0 to t 1 minus cos 2 omega t upon 2 dt. Let's solve this. H is equal to epsilon naught square upon r, and this is 2r, 2 will also be a constant, then we get integral dt 0 to capital T minus integral 0 to t cos 2 omega t dt is equal to epsilon naught square upon 2r, and these values we get after integration is dt ka integral will be t and limit 0 to capital T, and for cos 2 omega t the integration will be cos का इंटीग्रल हो जाएगा साइन, सो वी गेट साइन 2 omega t upon 2 omega and the limits 0 to capital T. Now our task is to substitute the limits, first upper limit then lower limit, then we get, so after applying limit we get epsilon naught square upon 2r t minus 0 minus sine 2 omega capital T minus sine 0 and upon 2 omega. These are the values that we get after applying limits. On solving this we get epsilon naught square upon 2r, this is t minus 1 upon 2 omega, and within the bracket sine 2 omega t. Now omega is 2 pi upon t, so it will be sine 4 pi. Omega की जगह 2 pi upon t, t and t cancel, and it will be sine 4 pi minus sine 0. So sine 0 is 0, sine 4 pi is 0, so this value becomes 0, and we get H is equal to epsilon naught square upon 2r t minus 0, that means t. So this is the value for H, that means the heat dissipated for one complete cycle of that alternating EMF. Now if we assume that epsilon RMS is the root mean square value of that alternating EMF, then amount of heat produced by this much EMF in the same resistance capital R in the same time capital T will also be capital H, and is given as epsilon RMS square upon 2 upon R into T. So this is the heat dissipated by the EMF epsilon RMS when applied to a resistance capital R for the time capital T. Now these two values of heat dissipated should be same. So on equating these we can find the relation between epsilon RMS and epsilon naught. It implies epsilon RMS square upon R into T is equal to epsilon naught square upon 2R into T. On solving this, T and R will be cancelled out, and we can get epsilon RMS is equal to epsilon naught upon root 2, and by putting the value of root 2 it will be 0.707 epsilon naught. So this is the value of root mean square alternating EMF. It is 1 upon root 2 times of the peak value, or 70.7% of its peak value, or 0.707 times of the peak value of alternating EMF. So this was the required relation between epsilon RMS and epsilon naught. That's all for the video. For next videos, stay tuned and keep studying. Thank you.